Hello, welcome to our semiconductor education program. This is Vincent Chang. Today I'm going to continue our learning on the semiconductor, basics of semiconductor. An intrinsic semiconductor, part 1, bond model. So basically I'm gonna teach you 4 lectures around the fundamental semiconductor characteristics. So 2 lectures on intrinsic, which is undoped semiconductor, and another 2 lectures on extrinsic, that is doped semiconductor. So let's start with the intrinsic semiconductor. In the previous lecture, I explained why we chose silicon as the major semiconductor material. So this slide shows the comparison between germanium and the silicon on your right. So both are column 4 element on the periodic table. So for germanium, it's a high material cost, low band gap, which means it will cause the higher leakage current, and poor quality of oxide, which means it's not suitable for the mass device, metal oxide semiconductor device. But on the other side, when you see silicon, number 1 is a low material cost. So number 2 is the higher band gap, which will cause the leakage current become lower compared to the germanium counterpart. And it has the extremely high quality of silicon dioxide. So it's the best candidate for the MOSFET, metal oxide semiconductor, field effect transistor, which I will teach in other course. Crystal structure of silicon. Crystal structure of silicon. So the left-hand side shows the crystal structure of silicon, which is what we call the diamond structure. So if you ever learn the chemistry, then you will learn a crystal structure called phase center qubit. Phase center qubit. So basically, the diamond structure of silicon are composed of the 2 phase center qubit structure, and it's kind of intertwined together. So now let's look deeper on the crystal structure. The side, so it's a qubit, right? So each side is the same. And the A is called the lattice constant. It's called lattice constant. So for silicon at the room temperature, the lattice constant is 5.43 angstrom, which is also equal to 0.543 nanometer. And then this is the left-hand side is the unit cell. So because it's a periodic structure, right? It's a periodic lattice structure. So let's just focus on the unit, okay? So let's focus on the unit. So let's translate the green to your right as the orange, okay? And then how many atoms surrounded surround that, the green on your left or orange on your right? The answer is how many? 4, right? So think about this. This is the rectangle, okay? I don't know if I have some rectangle here or qubit here, but no, I don't have around me, but it's okay. So it's just imagine a box, a qubit, and then in the center there's the atom, okay? So there's a square on the top surface and the other square on the bottom, right? So basically the center atom is gonna form a 2 bond to a diagonal corner, all right? The diagonal corner. So see? So on the top surface, on top square, the 2 atoms is going to occupy at the diagonal corner. And then you kind of flip 90 degrees, okay? And go to the bottom. Go to the bottom. And then the other the other two diagonal corner will be occupied in this way, all right? And then in this, on your right-hand side, the height of the cubit is half of the A on the left-hand side. So it's the half A, the half lattice constant. I just want to make it very clear, all right? And now, so how small is the 5.43 angstrom, which is the lattice constant of silicon, all right? So this is from the picture from the actual photo from the scanning electron microscope, SEM. So you see, it's the 7 nanometer, right? So now the technology has advanced that we can kind of handle 7 nanometer, 5 nanometer, and even down to 3, or some company claim they can do the 2 nanometer. All right. So let me just quickly give you a big picture on what we can have. The semiconductor technology has evolved so far, right? Over the last 70 years. Over the last 70 years, so starting from the transistor radio, the transistor invention of point contact transistor in 1947, and then the vertical axis represent the circuit complexity. So basically, the first 50 years is before millennium, all right? So after millennium, to this point, we have gone through about 20-something years. So we went through the transistor radio, mini computer, PC, internet, mobile, and to artificial intelligence and 5G, all right? So, and then if you look the time around the 2020 or 2018. So in 2018 is the 7 nanometer FinFET. 2020 says the 5 nanometer CMOS, so, which means the complementary MOS. All right, so one of the co-founder of the Intel, his name is Gordon Moore. And then he found out, he observed, under the affordable cost, the number of transistor or the circuit complexity per unit area in the integrated circuit doubles. The number of transistor in the integrated circuit per unit area doubles in every 2 years. Or some version says in every 16 months. So this is the famous Gordon Moore's law, called Moore's law, right? So we talk about so in 2018 is the 7 nanometer FinFET. I don't know what version you are using for your iPhone. So from the title, from Silicon FinFET to iPhone. So if it's the iPhone 10, this is the iPhone 10. So iPhone 10 or above. For the iPhone 10, it uses this technology called TSMC. 7 nanometer FinFET, all right? So if it's the iPhone 12 or this one, a MacBook Air, all right? So this is the MacBook Air launched in 2021, used the ARM-based Apple silicon chip. They named it, Apple launched this one as, they call it M1 chip. So what's the technology that M1 chip has been using? It's the 5 nanometer technology, all right? So it's the 5 nanometer technology. But how small is the 7 nanometer? Or how small is the 5 nanometer? It's hard to imagine, right? So look at my, this is the air, right? See, this is my air. If I do this, all right? So you see my air? And you do the cross-sectional of the human hair. Now, human hair. Hair. What's the diameter of the nominal value of the human's hair? is around 80 micron. So the average diameter of the hair is around 80 micron. So which is the 10,000 times more than the 7 or 5 nanometer. All right? So that's how you can imagine how small the 5 nanometer or 7 nanometer is. So let's go back to the crystal structure of silicon and focus on the unit cell of the silicon, right? So again, each atom is surrounded by the equal distance of 4, all right? Equal distance of 4. So this is the three-dimensional. But for future discussion or learning or presentation, this is a little bit complicated. So let's try to simplify it to your left-hand side as the two-dimensional structure. So each atom is surrounded by the equal distance 4 atoms. And this is the two-dimensional view. Let's go back to the periodic table. So where's silicon located? Column 4, right? So here's the silicon. The 28 is the atomic mass. 14 is the atomic number, right? So 2, 8, 4. What does that mean? The first 1s orbit, 2 electrons. And then to the higher energy state, 8 electrons. The outside orbital there are 4 electrons in the outside orbital. Again, it's the 2, 8, 4. Red, blue, and then green. So the outside orbital is called valence orbital. And the electrons sit in the valence orbital are named as a valence electron. All right? So valence electron 1, 2, 3, 4. So there are 4 valence electrons for each silicon atom. Right? So now, let's try to expose the 4 valence electron. And look at your left-hand side. So if we pull out the 4 electron, because the atom is neutral. So if we pull out the 4 valence electrons, each electron carries the 1 negative fundamental electronic charge, right? So the negative 1 represent the fundamental negative fundamental electronic charge. So the inside becomes the positive 4. So the positive 4 represent the positive 14 minus plus the negative 10. Okay, so put down this on the positive 14 plus negative 10. What do you mean by the negative 10? So on the first orbital is negative 2, but the second is negative 8. So this one, the positive 4 on your left-hand side represent is the simple explanation, illustration for the orange circle on your right. I think you get this one, okay? You got this. And now, this is the neutral. And then let's pull in the 4 neighbors. Let's pull in, but each one also contribute to the center. The original is green, right? So each one, let's say the 3 o'clock one contribute another electron, its own valence electron. And then the one on the 6 o'clock contribute another its own blue. All right. So now each pair. So the 2 valence electron, each atoms contribute 1. Each atom contribute 1. So both electrons pair forms a bond. So this kind of co-sharing. So co-sharing the valence electron is called covalent bond. So this kind of bonding is called covalent bonding. Okay, so at the room temperature, this is what we see at the absolute zero. In absolute zero temperature, all right? So this is what you see, what we see. What does that mean? So all the bonding are occupied. All the valence electron sit in, rest in the covalent bond, within the covalent bond's confinement, without any thermal energy. So in this condition, the material behaves like an insulator without any ability, any capability for conduction, for current transport. So this is actually an insulator. But when temperature is increased, let's say at the room temperature, 300 Kelvin. So if it's room temperature and then something changed, as you can imagine, when at room temperature, when temperature increase, so you go to the stove and then you got burn. What does that mean? Why there's a strong interaction between the stove and your finger? Why? It's lattice vibration, all right? So when temperature increased and then lattice vibration. So when lattice vibrate, the bond will be broken. So one of the bond will be broken. But from the other perspective, I will explain in the next lecture from the energy band perspective. When the valence electron gains enough energy from thermal, it's hot, and then the electron can jump out of the confinement, the bonding of the covalent bond, and become free, like this way. So if the bond is broken or electron absorb enough sufficient amount of thermal energy, they can jump out of the covalent bond, becomes free, all right? Becomes a free electron, we call it conduction electron. But in the original spot, where the electron sit, originally a space, an empty seat is left there, okay? So this kind of empty seat can cause the electrons surrounding the seat and then to competing each other to see which electron can occupy, can take the seat, can take the spot. And then the process of electron taking that spot can be equivalently translated to the seat going backward in an opposite direction. Okay, so in quantum mechanics physics, the researcher found out, instead of describing the complicated behavior of electrons competing each other to get to take the empty seat, it will be much easier to just track the trajectory, the behavior of the seat, the spot. All right. So that spot, the empty seat, can also equivalently to be pictured as a positive charge carrier. And that positive charge carrier is called hole, all right? It's called hole. So this kind of process is called, look at the subject, it's called thermal generation. So generate what? The electron-hole pair is generated, right? So again, at absolute zero temperature on your left-hand side, the material behaves like an insulator. But when temperature increases to the room temperature, then the material functions as a semiconductor, right? So what's the fundamental other characteristic that semiconductor behaves? So I will explain this in the future lectures, right? So I hope you receive something from this lecture. In the next one, I'm going to explain the energy band structure, energy band diagram, and the so-called band gap for the intrinsic semiconductor. So look forward to see you in the next one. Thanks for watching.